So we're starting now transistor biasing. Okay. So so far we discussed that if you want to keep operating point in active region, so we need to make your input as a forward bias and output as a reverse bias. Okay. So we have used two batteries separately. Okay. To keep the operating point. Okay. Where we want to keep, we want to keep in active region, we want to keep cutoff region, or we want to keep in saturation region. Okay. So at least we need two batteries. Okay. Now what is the purpose of biasing? Okay. So the purpose of biasing is number one point. Okay. Suitably to fix the operating point suitably. Okay. We want to fix the operating point. For that we need biasing का मतलब है you need some voltages. Okay. To apply you need some applied external voltages to need to be applied. Okay. To operate transistor. Now once we have stabilized the point, once we have fixed the point. Okay. Now the other challenge is there. When we have fixed the point, but transistor parameters, they vary with the temperature. They are function of temperature. Okay. So for example, your IC varies with temperature. So the second aim, okay, the second purpose of biasing is to keep check. Okay. To keep check on IC value. Okay. But in other words, in order to stabilize collector current. Okay. IC is your collector current. So if there is a increase of temperature, okay, so your IC will change. Okay. Why IC will change? So if you increase the temperature, when I have discussed the IV characteristics of a diode, okay, and I told you if I increase the temperature, okay, so once we have to increase the temperature, the first thing is what increases it increases your beta. Beta is a function of temperature. Okay. Similarly, if you increase the temperature, your ICO, reverse saturation current, that also goes up, increases. Okay. And I told you that the built-in potential VBE also goes down. Okay. So if beta increases and your IB is fixed, so increasing temperature directly affects IC. So your IC will go up. Okay. Your ICO increases, ICO will also add in IC. So your IC will also increase. Similarly, VBA decreases in forward bias, that will increase your IB. Okay. And then the increase of IB again result in increase of IC. So you have this IC also increases once you increase the temperature. So temperature, so you need to make your circuit, okay, such a way that it should be as far as possible independent of temperature. Okay. But temperature, your operating point should not shift uh, from the region where you are suitably fixed. Okay. So in order to do these things, okay, we need to apply proper biasing. So biasing should be such that which stabilize the current IC, and which fixes our operating point. Okay. But now this is the one aspect. Okay. That is technological aspect or engineering aspect. Okay. There are other sub commercial aspects also. So I told you, in order to give biasing to a transistor, I have given two batteries. Okay. Now on a chip, okay, say we have 1,000 transistor, or somewhere we have 100 transistor, okay, on a board. So we can't keep on giving two batteries to each transistor. Okay. So that become very costly. Okay. Batteries are very costly. So don't want to raise the cost of your equipment. So, and similarly the maintenance of battery is not easy. Okay. So this is a engineering aspect. And third thing is, okay, you don't want to use batteries are costly. So you don't want to use so many batteries. Okay. Batteries are costly. Okay. Okay. And then maintenance also difficult. Maintenance, okay, of battery, maintenance of battery, okay. And even your chip transistor, if suppose some one transistor become bad, okay, become a malfunction, and then you want to replace some other transistor or some other transistor. Now that other transistor may have different parameters, okay. So that means even you using so many transistors, they don't not exactly similar, okay. Their variation may be for VBE or in their beta value, okay. So once you change, you put another instance, it would automatically destabilize your circuit. So our biasing should be such that is always keep check on IC and always try to fix my operating point, okay. So maintenance of battery and transistors are difficult, okay. Is challenge, transistor is challenge, okay. So now in generally what we have so many transistor, but we have only one battery, and through this one battery we give biasing to the input output of many transistors, okay. So there are variety kind of biasing. Each biasing has there is a their own disadvantage or advantage, okay. So mainly we'll start with some elementary biasing, okay. So elementary biasing is your first biasing is your fixed biased, okay. So that is not a good one biasing, but that is a elementary biasing, okay. So we're starting with a fixed biasing or fixed bias circuit, say fixed bias circuit, okay. So fixed bias circuit means you have, I'm erasing this one, okay. So I'm using only common ammeter configuration here now onwards, okay. So you have a battery VCC, okay, okay, and here we have a resistance, say RC, and here you have one more resistance is going through. Just 1 minute. Okay, so we have a transistor, okay, and we have, say, a biasing here, and here we have a transistor VCC, okay. So I call this is RC, and there is a one more resistance here which I call RB. So this is a very elementary type of biasing. So this is elementary biasing. Elementary biasing means this biasing is not good. That means it cannot keep check on your current ICC. Okay, so if temperature increases, your IC will increase. So I'm applying VCC here. Okay, and when I apply VCC, obviously my, okay, so this is a circuit. Now you need to, so here we have two loops, okay. Say this is my input loop and this is my output loop. Now as you can see, I'm only giving one battery, okay. So when I keep like battery like this, okay, that means battery is like this is like this, okay. When plus is there, so this is the battery is like this, and other part of battery is grounded, negative is grounded, negative is grounded, okay. So this is grounded. When I plot like this, you understood this is a plus and negative is grounded, okay. Negative liquid ground, you can put battery here and you can keep here, because I want to show this battery is connected to both input and output. That's why I am drawing this battery like this, okay. Is clear? Any confusion? Okay, now just you have input loop, you write the equation for KVL through this input loop like this, okay. And similarly you write KVL to this output loop. You know here voltage is VB, okay. So I can write, okay, minus VCC plus, say current is flowing, this current is going to base, so obviously this current should be IB, okay, and this current is going through collector. Okay, just check, this current is IC, whatever current enters in the collector terminal, that is IC. Okay, so this is IC, so obviously IC is flowing here, so I have IB/RB, then we have voltage drop VB, okay, and then we have 0, and from here I can find my IB. Okay, IB is nothing, VCC minus VB, like yesterday we were done, divided by RB. Okay, now once I know the IB, okay, I can find IC using beta IB. Okay, and similarly if I write it in collector loop, so this is minus VCC plus IC RC. There is no other resistance in the circuit, so I can just take this one. Okay, so ICRC equals to, and then plus VCE equals to 0, and this gives me VCE equals to VCC minus ICRC. Okay, now these are, you have two equations. Okay, so this is your equation 1, this is equation 2. Okay, using this thing you can find, okay, your operating point. Okay, whether it is a active region or saturation region. But one thing is, you can see here IC is not independent on beta. Here IC dependent on beta. If there is a temperature variations, okay, then your beta will change, your IC will change. Okay, so that is not a good biasing. Okay, because it's not able to keep check on your IC. Okay, but just for starting we are doing this one, and of course in order to find the operating point you always need to calculate IC saturation. Okay, IC saturation, which is nothing, you need to make VC 0, the IC saturation is just VCC upon RC. You put VC 0 in this question, this will be IC saturation. Okay, so this is say third, and say this is fourth. Okay, these equation you need to use. Okay, let me give one problem. And of course yesterday we discussed the operating point is Q. Q is what? Q is your VCE comma IC. This is your operating point. Okay, so in the question, your this RB is given 270 kilo ohm. Okay, and RC is given 2.2 kilo ohm. Okay, VB you can take 0.7 sometime, because VB is generally very less compared to VCC. Okay, so sometime in exam they tell you that neglect the VB. Okay, or you can, even you take VB is 0, your nothing much will change in the answer. Okay, just for accuracy you have to take VB 0.7. Sometime you may take it, you can take it as 0 also. So VB is given and you have been given beta value. Okay, so beta value is given to 50. Okay, so please find out the operating point. Okay, so IB, first you need to find the IB from the input circuit. Your VCC I didn't give.
तो VCC कितना दिया हुआ है?
तो पूछ ही नहीं रहे हो. VCC 9 volt. VCC is 9 volt. VCC is 9 volt. Okay, so VCC is 9, 0.7. RB is your 2.2 kilo ohm. This gives you 9.0 minus 0.7, 8.3 upon 2.2 into 10 raised to power 3. Okay, so that will give you the value 30 microampere. Okay,
सर 270 रखेगी ना वैल्यू? 270
कौन सी 70?
सर आरबी
आरबी, हाँ आरबी 270 किलो ओम, सॉरी आरबी इज 270 किलो, 270 किलो, 270 किलो
30 मिली एम्पियर
मिली एम्पियर है कि माइक्रो एम्पियर है?
सॉरी माइक्रो एम्पियर
So 30, there should be answer should be 30 microampere. Okay. Now once you know the IB approximately, now you know you can calculate the IC. So IC will be simply 50 into IB, 50 into 30 microampere. Okay. So this becomes how much? 1.5 milliampere. Okay. So you have now IC value 1.5 milliampere. You can calculate IC saturation. Okay. IC saturation is nothing BCC. Okay, 9 upon RC. RC is your 2.2 kilo ohm. Okay, how much is coming? Should come around 4 milliampere.
4.09.
4.09. Okay, so 4.09 milliampere. So your IC is less than IC saturation. Okay, so obviously the operation region is active. Okay, and other things you can calculate VCB. You want to recheck, just like you done, you can recheck. Okay, finding the value of VCE and then VCB plus VB, you know. Okay, so now just find the VCE. Okay,
5.6.
VCE will be your VCC 9 minus IC. IC you have just now calculated how much? IC was how much? IC value
1.5.
1.5. IC RC is your 2.2 10 raised to power 3. Okay, now you can solve this one. Milliampere, IC was milliampere and this kilo ohm, so power cancel. Okay, so 9 should come 5.7. Okay, good. So 5.7 volt is coming. Okay, now you know the VCE, you know the VBE, you can find out VCB. VCB is still positive, so NPN times say VCB should be positive. That means it's a active region. Okay, so this is circuit, no issue. Okay, so this is your operating point. So operating point Q will be simply your VCE that 5.7 volt, and IC is your 1.5 milliampere. This is your operating point. Now, but as you can see, this, if there is this variation of beta in the circuit, okay, if there is a variation of beta in the circuit, then obviously your IC will change, and you want to fix it on active region, it may go in saturation also. Okay, so that's why this biasing is not good. For example, if I give you a question, okay, suppose if temperature increases and beta varies, okay, from 50 to 150. Okay, for example, a question where beta is varying from 50 to 150. Okay, that means in one case you can take beta 1 as a 50, and second case you can say beta is 150. Okay, and same RB I'm taking now 300 kilo ohm. Say RB is 300 kilo ohm. Always see this RB will be always greater than this RC. Okay, so say RB is 300 kilo ohm and your RC is say 2 kilo ohm this time. Okay, VB let us take 0.7. Okay, VB take 0.7 or VB also you can take 9/3. Okay, so this time you take VB is 0. Particular question, you take VB is 0 volt. Okay, now calculate operating point and ratio of IC2 versus IC1. Find a ratio of IC2 versus IC1 in these two cases, and tell me what is the region of operation and region of operation, okay, and what is your operating point. Okay, so obviously when you increase the beta from 50 to 150, if okay, then things change, okay, dramatically, and your transistor goes from active to saturation region. Just check it, calculate and tell me the values and operating point for these two cases. Two cases means one case you have beta equals to 50, other case you have beta equals to 150. Other things are same, calculate and tell me the ratio. So I am not solving this one, you need to tell me what is the operation in first case. So case first, when your beta 1 is 50, in that case what is the operation region? Okay, what is the operating point? Okay, finally you need to calculate IC1. What is the value of IC1, and then you have to find a ratio also, IC2 to IC1. So
for 51.3 milliampere and for 154 milliampere.
1.3 milliampere क्यों आएगा? VB 0 लिया ना इस बार?
सर 0.7
मैंने हाँ कोई ओके देन ठीक है, मैंने 0 नहीं बोला था, वो भी सही आंसर ठीक है. ओके, तुम मे बी 0.7 से करो, कोई इशू नहीं है, कर दिया तो. ओके, सो एंड फाइंड
Sir,
यू
1.5 milliampere or 4.5?
yes. So in first case your IC1 will be 1.5 milliampere, and second case your IC2 will be 4.5 milliampere, and if you take the ratio will come 3. Okay,
सर IC saturation आ रहा है इतना 1.5 और 4.5.
हाँ वेरी गुड, सैचुरेशन आएगा ना फर्स्ट केस में सैचुरेशन नहीं है. ओके,
सर 4.
what is the value of saturation? 4.5. So first case there is no saturation, so in first case what is the operation region? First case what is the operation region? How to find operation region? Okay, IC saturation in first case. Okay, you have IC1 is equals to 1.5 milliampere, and IC saturation is what? IC saturation is your 9 upon
6 volts.
9 upon
2
what? 9
kilo.
upon what? 2 kilo ohm. 2 kilo ohm. Okay, so 2 kilo ohm, so that will come 4.5 milliampere. So in first case your IC is less than IC saturation, so obviously you have operation region is active. Very good. And operating point you are saying 6 volt and 1.5 milliampere. Very good. This is the first case. Okay, in second case second, you have beta equals to 150. Okay, IC2 you already told that is 4.5 milliampere. Okay, and your saturation current also same IC, so your transistor is in saturation this time, so the operation region is second case, operation region is your saturation. Okay, and operating point Q will be whenever you are in saturation, your VC becomes 0 and your current become equal to actually saturation 4.5 milliampere. Okay, so you can see this kind of circuit is not suitable because this if you beta changes in the circuit, okay, it cannot stabilize your operating point. Operating point goes from active to saturation region. Okay, so I hope the point is clear. Now we'll go some other kind of biasings. Okay, so you want to do more problems or is it fine? This biasing is fine. Okay, you can do it. So I'm giving one homework. Okay, you try that homework. So same for fixed bias. I'm giving you RB value. RB value I'm giving you 100 kilo ohm. Okay, beta value I'm giving you 150. Okay, RC value I'm giving 1 kilo ohm, and you can take VB 0. VB 0. Okay, you need to tell me. Okay, this homework. Okay, find the operating point. Operating point and second reason of operation. Homework. Now next biasing is collector to base bias. Okay, so the next biasing is collector to base bias. So collector to base bias means you have your transistor. Okay, you coming here, RC is coming. Okay, and from RC this time not taking this side, taking this side. Okay, you have a resistance RB, and RB is going directly to here. Okay, and this is your grounded. This is your VB. Okay, so here this is your IB and this is your IC. Okay, clear? So what is this current? What is this current? What is this current? If this current is IC,
IB plus IC.
IC plus IB.
very good. So this current is your IB plus IC, and this is your VCC. Okay, so this is your collector to base bias. So collector to you going here. Okay, so you have to keep this current always. Okay, here current, whatever current goes in collector, that is IC. Whatever current is going base is IB. Accordingly, you have to write what current is flowing here. Okay, total current is IB plus IC. Now again you have a two loops. Okay, input loop and you have output loop. Okay, just write the equations. So again, if I take this loop, I same equation, I got VCC plus IBRB. Sorry, this time I have a IC also. Okay, so I have now this time minus VCC plus IB plus IC into RC. Okay, I'll come this time this way, plus IB RB, okay, plus VB equals to 0. So this is the equation now, but I want to calculate only IB from input circuit, but here IC is coming. So what should I do?
Beta IB.
Very good.
IC
Okay,
by beta.
Very good. So you can put IC equal to beta IB. Okay. So you can write now minus VCC plus IB RC. Let it be IB, and this will become beta plus 1, IB common, RC common. Okay. And then you have a IBRB, and then you have a VB. Okay. So you can simplify this one, and you want to calculate IB. So your IB will be, okay. So your IB will be what? VCC minus VB. Okay. Then IB, if you're taking IB common, so here's RB plus beta plus 1 RC. Okay. Is it fine now? Check it, whether the formula is correct or not. Okay. So if the formula is correct, okay. Now this is your input loop, and you have your IB value. I'm writing here. IB value is VCC minus VB upon RB plus beta 1 plus RC. Okay. Now, what is the advantage of this circuit? Can anyone tell me? What is the advantage of this circuit? Just look at the expression. Okay. Compare with earlier configuration, earlier fixed biasing. You say now IB also depends on beta. So whenever temperature goes high, okay, your beta will increase, and then beta will increase the IC. But you same time you see beta also here present. So as beta increases, your IB will go down. Are you getting? So this kind of circuit is indirectly keeping check on IC value. So obviously it will not keep perfect check for this circuit. We'll go, we will go in improving. Okay. Actually, we need to make IC independent of beta. So far it is not independent, but your IC now, if I write IC, okay, so IC will be my beta IB. So beta increases, my IC increases, but beta increases, same time your IB also decreasing. Okay, so there is some kind of check. Okay, this circuit is trying to reduce the IC. Okay, so that's kind of the advantage of this circuit compared to previous circuit. So what basically is happening? Okay, let me explain. So in this circuit, what happens if temperature increases? Okay, if temperature increases, your beta will increase. Okay, beta increases, what will happen? Automatically your IC will increase. Okay, IC will increase. Now IC increases, then this voltage drop VRC will also increase, isn't it? So your VRC, okay, VRC, that is drop across resistance C, RC, VRC will also increases. Once VRC increases, the drop increases, the voltage this point decreases. So you can say your VC is decreasing, VC at this point. If the voltage this point decreases, obviously your IB will decrease this point voltage, because IB is what difference of this and this voltage. Okay, so when VC decreases, automatically what happens? Your IB decreases. IB decreases. Once IB decreases, automatically what happens? Your IC decreases. Okay, IC decreases. So there is some, okay, limitation this circuit is applying okay, to keep check on IC. So because beta is there in the circuit, so this have some control compared to that one. Okay, so this was input loop. It is point is clear what I'm saying, or you can put one more step here. We will understand.
Sir,
If VC decreases, okay, VC decreases, then what will happen here? The voltage drop VRB will VRB also decreases. VRB, okay, VRB decreases. Now RB is fixed, VRB decreasing, that means your IB decreasing. Okay, IB decreasing means your IC decreasing. हाँ बोलिए, tell me now.
sir, VRC is increasing, then VC is decreasing.
Yes, VC.
Sir, means voltage across
अरे भाई
IC.
yes, some voltage is there. Now if IC increases, okay, this voltage drop will increase obviously.
Yes, sir.
With this voltage drop, because IB is negligible compared to IC, so mainly
Yes, sir. Yes, sir.
IC flowing. So this voltage drop is increasing, that means this point will decrease, na?
Yes, sir. Yes, sir. Okay,
So
sir.
this point voltage decreasing, that means your this voltage decreasing, that means your VRB now less current will flow here. So VRB decreasing means your RB is fixed, your IB decreasing, or you can say simply from here beta increases, your IB decreases. Okay, IB decreases, again it controls IC. That check is not perfect, but it has some control. Okay, now shall I erase this one? Okay, now this was your input loop. You can write the equation in output loop. Output loop, what is happening? You have minus VCC plus IB plus IC into RC plus VC equals to 0. And now your VC is equals to what? VCC minus IB plus IC RC. Okay, now this equation will keep unchanged because IB is negligible compared to IC. IB will be microampere, this will be milliampere. So exit calculation you do it like this, okay, but you practical purpose you can always leave this IB compared to IC, because IB is less compared to IC, so you can write RC, so your equation remains same in output loop what was earlier, or for exact calculation you want you can put this equation also. Okay, and remaining calculations are same what are doing. Okay, so let me do one problem. So RC is given 500 ohm. RC is given 500 ohm. Okay, and RB is given 500 kilo ohm. RB is given 500 kilo ohm. Okay, VB you take 0. VB you take 0. Okay, and then VCC is given as 10 volt, and okay, beta value is given 100. Calculate the operating point and operation region. Tell me what is the IB value? What is the IB value?
Zero 0.196 microampere.
No. 0.19. 1.8 something coming.
So yes, sir. 1.8 into 10 to the power minus 5.
1.8, 5 or 6.
सर -6 तो आ रहा है पर 1.9 आ रहा है.
So I have answer 1.86 microampere. Or 1.5. 1. What are you getting? 1.8 into 10 raised to power minus 5.
6.
Yes, sir.
Okay, let it be like this. Okay. So IC will be how much? IC will be 1.8 milliampere because beta is 100, isn't it? Okay, correct. So now you have, and if you find IC saturation will be same. You keep VC 0. Okay. This time you can neglect this current compared to IB. You can neglect compared to this one. You have just simply VCC. VCC is your 10 upon RC. RC is your 500 ohm. Okay, so this become 20 milliampere. Okay, so operation region is active. Okay, and VCE VC will be 10 minus ICRC 1.8 into your RC is 500 ohm. Okay, so this becomes say 10. This is a milliampere. Okay, so 0.5, so 10, say this is 0.9. Okay, so this should come 9.1 volt. Okay, so your operating point will be 9.1. IC is 1.8 milliampere. Now I have given you one question. We have solved one question of fixed bias where I have given you value of RB and RC. Okay, so and I told you that calculate the ratio of IC2 by IC1. Okay, the same question I'm giving you again. Okay, you take RB equals to 300 kilo ohm and RC 2 kilo ohm, and beta 1 is equal to 50 and beta 2 is equals to 150. Okay, RC value is 2 kilo ohm. Okay, you can take VB 0. Okay, BCC is like same like earlier 10 volt. Okay, same like a last question, but that was a fixed bias. This is a collector based bias. Resistance values are same and beta I'm giving same, and then you have to find out IC2 by IC1 like yes you done for just that case, fixed bias case, and you have to compare that case. So there we got a ratio IC2 by IC1 as a 3, and you have to see check here how much is getting. So you'll find this biasing is comparatively better, even though same beta is changing, beta range is same with temperature, but the variation of IC is less in this particular question. Okay, so this is your homework. I'm doing next biasing. Okay, shall I raise this one problem? Have you written the homework?
Yes, sir.
Yes, sir.
Now the next biasing is your
Sir,
ammeter. Yes,
सर उसमें IC saturation नहीं find करना है.
करना है ना, इसमें भी करना है.
IC2.
किसमें? हाँ वो किसमें? पहले क्वेश्चन में
जो होमवर्क क्वेश्चन है सर।
उसमें IC1 IC2 दोनों कैलकुलेट करना है ना।
हाँ, वो IC
दोनों
सैचुरेशन है ना।
हाँ, IC सैचुरेशन में कैलकुलेट करना पड़ेगा, तभी तो कंपेयर करोगे ऑपरेशन रीजन क्या है और रेशियो, ऑब्वियसली एवरीथिंग, ऑपरेशन रीजन क्या है, व्हाट इज द रेशियो, हाउ ऑपरेटिंग पॉइंट इज वेरिंग, यू टू चेक। ओके,
ओके सर।
गुड।
ओके।
Okay. So ammeter feedback bias circuit. Ammeter feedback bias circuit. So ammeter feedback bias circuit is okay, same like your fixed bias circuit. You have a RB, you have a RC value. RC is going your to your ammeter. RB coming here, and just we have a one more resistance here, RE. Okay. Now things slightly changes. Okay, now this is your VCC. Okay, and this is your, again this is VBE, this is your VCE. Okay, now if I write the equation, the equation will be what? Minus VCC plus IBRB. Now current is going here, this current is IB, and this current is your IC. Always see the same current is going here, so this is IC, same current going here, this is your IB. IBRB plus VB. Okay, now here you have RE also. So RE, so this IB coming here, IC coming here, so obviously here IE is flowing. Okay, so you can write IE RE equals to 0. Okay, now IE equals to what? IE is equals to IB plus IC. Okay, and this is IB, IC is your beta IB. So I can write I equal to beta 1 plus IB. Okay, and beta is very high, so you can also neglect 1 if you want. Okay, so this is your IE. So this IE I can put here. So I have now minus VCC plus IB RB plus VB plus beta plus 1 IB RE. Okay, and this will give me the value of IB is equals to VCC minus VB. Okay, then I have, if I take IB common, then this is RB, and then you have a beta plus 1 RE. Okay, so beta, you know IB, you can find IC keeping beta IB. So here also there is a check, you have beta is keeping check on your IB. Okay, so this is your input equation. Similarly, you can write the equation for output. Now output, there is slight change. Okay, because now RE is there, and you have to keep in mind now your IC saturation formula will also change. The method is same for IC saturation. आपको क्या करना है, जैसे IC saturation निकालना है, आपको VCE को 0 कर देना है इक्वेशन में, आउटपुट इक्वेशन में VCE को 0 कर देना है. इस टाइम फॉर्मूला चेंज हो जाएगा IC saturation का भी. ओके, so write for equation for second loop. Okay, so let me write now for
IB की
second.
वैल्यू मत बताइए.
So now for output loop, what you can write, same, minus VCC plus ICRC plus VCE, okay, plus IE RE, okay. So now you want VCE, so VCE will be what? VCE will be your VCC minus IC RC plus IE RE, okay. Now always your IE is also equal to IC, so here you can take this is RC plus RE
माइनस
IC.
आई आ रही होगा ना,
कौन सा?
VCC माइनस.
So this will become, because your IC is almost equals to IE, so you can keep IC equal to RC in the expression for simplification, okay. And in this particular question, IC saturation, okay, IC saturation, you again go to VC is 0, so this time the formula of IC saturation will be your VCC upon RC plus RE, okay. So I'm giving one problem. IB is given, okay. So the value of RB is given as 10 kilo ohm, okay, and the value of RC is given 75 kilo ohm, okay. VCC given 6 volt, okay, and your RE is given 100 ohm. RE is given 100 ohm, okay. Beta is 50, okay. So first case you take beta equals to 50, and in second case you take beta equals to 300, okay. And both the cases you have to find out the operating point, region of operation, operating point. Calculate. So
सर VB 0.7 लेना है, 0 लेना है.
VB you can take 0.3 in particular question, this question 0.3, okay. So it's germanium, VB is 0.3, okay. So if VB is 0.3, okay, so I'm giving the answers, okay. Now we have already done same, okay, repeating process there, so I'm giving the answer, okay. You need to check, you need to solve and send me. So IC value in the first case I have I have 18.5 milliampere, and the region of operation is active because my IC saturation value is high, okay. How much is there you need to calculate, okay. You tell me. Operating point Q is what? Operating point this time is, you have 2.69 volt, okay. There will be slightly change that you can correct, and this is about 18.5 milliampere. This is the first case. Second case you have to calculate region of operation IC at this one, okay, and that is your homework. Similar type of calculation hai, okay. You practice, then once we finish this one, then we will do exam problems also. Okay. So I'm stopping here. If you have doubt, please ask.